Welcome to Bite Size Tutorials, where we break down complex topics into quick, easy to digest lessons. Today, we will talk about replication. Replication is the process of copying data from one server to others so that your data can be more available, reliable, and resilient to failures. It's like making copies of an important document and keeping them in different locations. If something happens to one copy, you still have backups. But in the world of databases, replication comes with its own trade offs. And to understand it properly, you need to know two things: how the data is replicated and how the servers are organized. Let's start with how the data is replicated. There are two main ways: synchronous replication and asynchronous replication. In synchronous replication, when you write data to the main server, the system waits until all the replicas confirm they have the data before telling you that the write is complete. This guarantees that all replicas are always up to date, but it comes at a cost. If even one replica is slow or unreachable, your write will take longer. It's like sending a message in a group chat and waiting for everyone to say got it before moving on. Systems that need absolute consistency, like banking or healthcare systems, prefer this method because this data must be accurate at all times. In asynchronous replication, on the other hand, the main server does not wait for the replicas. It confirms the writes immediately and then sends the updates to replicas in the background. This makes writes fast because you are not waiting for everyone to catch up. But there's a catch. If something goes wrong, like a network failure, some replicas might never get the latest updates. This makes asynchronous replication faster but less reliable when it comes to consistency. Systems that prioritize performance, like analytics platforms or global systems where writes happen quickly, use these methods. Now, you might be wondering, if asynchronous replication doesn't wait, how do systems ensure consistency? This is where eventual consistency comes in. Eventual consistency guarantees that even though updates are sent asynchronously, all replicas will eventually have the same data if you give the system enough time. It's like mailing out invitations to a party and knowing that no matter how slow the mail is, everyone will eventually receive their invite. To make this work, systems use retries to resend failed updates, rules to resolve conflicts when replicas disagree, and periodic checks where replicas compare their data and fix any differences. This is how systems like DNS servers or global distributed databases ensure that data stays in sync over time. With that understood, let's talk about where the data is stored, which brings us to the three main replication architectures. The first is single leader replication. Here, one server called the leader handles all the writes. The leader then sends those updates to its followers, which act as read only replicas. This setup is simple and guarantees consistency when paired with synchronous replication. But it has a limitation. If the leader goes down, no one can write data until a new leader is elected. This method works well for systems with lots of reads and fewer writes, like websites where users mostly browse content and write content very less. The second architecture is multi-leader application. In this setup, multiple servers can handle writes and they synchronize with each other. This is great for systems that are spread across different locations because each region can have their own leader, making writes faster for users nearby. However, multi-leader application comes with its own challenges. For example, conflicts. If two leaders accept conflicting writes, the system needs a way to resolve which one is correct. It's like two people editing the same document at the same time. You need rules to decide whose changes to keep or how to merge them. Systems like collaborative tools or global platforms often use multi-leader replication because low latency is more important than perfect consistency in those cases. The third architecture is leaderless replication. Here, there's no single leader. Any server can accept writes, and changes are sent to other servers using clever mechanisms like quorum based replication in a quorum system. A write is considered successful only when a majority of servers agree. This makes leaderless systems very fault tolerant because there's no single point of failure. Even if a few servers go down, the system can still keep running. However, managing consistency in leaderless systems is harder and they often rely on eventual consistency. This architecture is used in large scale systems like Cassandra or Amazon DynamoDB, where availability and scalability matter more than strict consistency. To tie everything together, replication is about making data available and reliable, but it involves trade offs. Synchronous replication gives you strong consistency but adds latency. Asynchronous replication is faster but leaves replicas temporarily out of sync. Eventual consistency ensures that even with asynchronous replication, all replicas will converge to the same state over time. Single leader application is simple and consistent but has a single point of failure. Multi leader application reduces latency but adds complexity with conflicts. Leaderless replication is fault tolerant and highly scalable, but sacrifices strong consistency for eventual consistency. In the end, choosing the right replication strategy depends on what your system values most. If you're running a financial system, a strong consistency with synchronous single leader replication makes sense. If you're running a global platform where speed and availability are critical, you might go for leaderless replication with eventual consistency. Replication is a balancing act, and understanding these concepts will help you design systems that meet your needs for performance, consistency, and reliability.